In this PhysCast, we're going to calculate some expectation values based upon a particular wave function. In this case, we're going to be looking at the expectation value of position, x, and the square of position, x squared, for this wave function here, basically a Gaussian wave function. Now, whenever we're calculating expectation values, it's important that we know that our wave function is normalized. So the first step we might do here is to normalize this wave function. To normalize a wave function, we're going to take the integral over all space, so we'll go from minus infinity to plus infinity. We're not told anything about whereabouts this particle exists. It could be anywhere from minus infinity to plus infinity, dictated by this wave function. And then we do the complex conjugate of the wave function, psi star, multiplied by the wave function. That's the integral we need to do. And to normalize, we actually need to set that integral equal to 1. So we need to figure out how to calculate that. So let's do this integration from minus infinity to plus infinity of the complex conjugate. So we have to conjugate everything in here. That would be a star, but in fact we don't need to do that because we're told that a is a real constant. So a star and a will in fact be the same thing, but we need to make sure we're aware of that. Then e, it would be to the minus b star, but again b we're told is real, so that can just be b times x squared. But this minus I omega t, again omega is real, so the complex conjugate of that will be plus I omega t. So there is actually psi star, the complex conjugate of my wave function, multiplied by my wave function, a e to the minus b x squared minus I omega t, and that's the integral that I need to do. Now there's a few things I can do fairly easily here. I can pull a times a out the front, a squared, integral from minus infinity to plus infinity. And now when I do this e times this e, I'm just going to add the exponents. So I'll get minus 2bx squared, and I'll get I omega t minus I omega t, which of course cancels through to give me 0. So there's nothing else in my exponent there. That's the integral that I want to do. Now, one thing when we're doing these kinds of integrals that we might think about is if we're integrating symmetrically about the origin, we're going from minus infinity to plus infinity, then what kind of symmetry does this function in here have? And you should be able to see that this is actually an even function in this case here. What do we mean by that? We mean by that if we took the function of some value of x, we'd get exactly the same value if we took the negative of that x. You can see this thing only depends upon x squared. So it doesn't care whether it's a positive or negative x, so it's definitely an even function. And one thing that makes me do that's a little bit of a simplification is instead of integrating from minus infinity to plus infinity, I can just go from 0 to infinity and double that. And of course I've still got my a squared there and my e to the minus 2bx squared dx. So it's a bit of a simplification, and it allows me to perhaps think about doing this integral here. I might actually kind of just look up a standard integral. That might be one way at least of doing this kind of integration. You might have other ways of doing this, but certainly having a nice table of integrals, or maybe have an online version of that. And the integral that appears in my handy book of standard integrals says that the definite integral from 0 to infinity, and the way they've written it in my book here is it's e to the minus a squared x squared dx. That turns out to equal the square root of pi divided by 2 times a. And in the particular integral that I'm doing here, this value of a squared actually equals 2 times b. Or if you like, the value of a here is going to be root 2b. And that means I can now do this integral here just by comparing it to my standard integral. I'm going to have root pi divided by 2 times the square root of 2 times b. And of course there's some simplifications to do there. This 2 cancels with this 2 here, and I'm going to end up with a squared multiplied by the square root of pi over 2b. Now remember, for my normalization I actually want that to equal 1. And that tells me that a squared must equal the square root of 2b over pi, or a, if I need that normalization value there, will be 2b divided by pi all to the power of 1/4. I'm taking the square root of a square root there. And that might be a useful thing to keep in mind. That's my normalized value for capital A in my wave function here. So I might just write it up the top here, because I'm going to be doing some more calculations in a minute. I might need to keep that in mind. Capital A here is 2b divided by pi, all raised to the power of 1/4. So I might clear my workspace here to do my next calculation, the actual calculation of the expectation value of x. So what does it mean to calculate the expectation value of x? We will often write that as, say, some angled brackets here with x, or you might see it sometimes written as x with the bar across the top. We're kind of meaning the same thing here. The expectation value we calculate by doing the integral over all space, so again from plus and minus infinity there, of the complex conjugate of our wave function, and then the quantity whose expectation value we're trying to calculate, and then the wave function. So that's the integral we need to do. And there's some steps in here that will look a lot similar to our normalization calculation that we've just done. So we should be able to pull out a factor of a squared out of this. You should be able to see that when I go from minus infinity to plus infinity in my integral here, the I omega t and the minus I omega t are going to cancel out, and I'm simply going to be left in here with x multiplied by e to the minus 2b x squared dx. So there's the integral that I need to do. Of course I can write a squared in terms of these other constants, but I'll just leave it like that for the time being. So we can again look at what's happening to this function that we're integrating symmetrically about along the x-axis between minus infinity and plus infinity. And you should be able to see there's kind of two factors in there. This one here that we already talked about as an even function. It was the same thing we looked at when we did the normalization calculation. But this one here, just x itself, you should be able to see is indeed an odd function. And by an odd function I mean that the value of the function at some value of x is the negative of the value at minus x. Of course that's a property that just x by itself has. Minus x is the negative of x. And we can probably look at that in a little bit more detail. If we kind of graphed out what kind of function this thing looked like, we might get a function a little bit like this. You can see if I just overlay this graph here, you can see that's actually a graph of that kind of function. It does have this odd behavior, an odd function multiplied by an even function. So this is actually a graph of this x times e to the minus 2b x squared. And that tells you if you're going to integrate all the way along the x-axis here, basically anything you get for your integral on this side will be the negative of what you get for the integral on this side. And you can see straight away, even without actually doing that or looking at the standard integral, which you could do, but you can straight away see here that this thing's going to actually come out to equal 0. So our expectation value of x here will be 0. Now you've got to keep in mind not all functions are even or odd. Some functions are neither of those things. So sometimes you really do need to do the integral, from first principles, but it's always worth having a look to see if there's some important symmetry information here that lets you do the integral much more straightforwardly. So in this case we can kind of see that we have an odd times an even function that we're integrating symmetrically around 0. So everything on one side of that axis there will be the negative of everything on the other side, so they'll exactly combine to give 0. So we might write up here that our expectation value for position in this case is actually exactly equal to 0. And now we might make ourselves some space and do the second calculation of the square of position. Where in fact all we're doing here, the only change we're making is instead of calculating the expectation value of x, we're going to calculate the expectation value of x squared. So we can just go along in this same kind of form here and put a little squared there everywhere, and it's going to look very similar, at least to start with, to our previous calculation. So here we'll have capital A squared out the front. We're going to integrate from minus infinity to plus infinity. Here of x squared e to the minus 2b x squared dx. Of course you might want to go and do this actually step by step to make sure you know exactly where this comes from, but it's the same process we did before. Once again, let's look at our function that we're integrating between plus and minus infinity. This one here, we've said several times, is an even function, and x squared, of course, you should recognize is also an even function. And we might just have another quick look at a sketch of that. And you can see here we do indeed, if I just outline again, this is a graph of that particular function, x squared e to the minus 2b x squared. And you can see whatever we integrate on one side there, we'll get exactly the same thing on the other side. So the positive and negatives don't cancel, but we can again use that simplification that we'll get twice the integral from 0 to infinity that we would have had going from minus infinity to plus infinity. Again, x squared e to the minus 2bx squared dx. So once more, here's our integral to solve. Let's look up a standard integral. Again, if that's the best way I can think of to do it. You might have other ways of doing it. Perhaps you'll use something like Wolfram alpha to solve this kind of thing, but I'll just look up a standard integral that tells me the integral here from 0 to infinity, the definite integral of that. In this case, it's written in my book here as x squared e to the minus ax squared dx. And an integral of that form, that definite integral there, is going to be the square root of pi, again here, now divided by 4 times a to the power of 3/2. And you can see that in my example here, this quantity a is actually going to be 2b for my example. So doing this again, I'll end up with 2 times a squared. Now this integral here will be root pi divided by 4 times 2b to the 3/2. And I might now write my a squared, because I know what my normalization coefficient is from a previous calculation. This is going to be, well, I'm going to be doing 2 times b over pi to the quarter, but I'm going to square that, so it ends up being to the half, multiplied by, let's just write pi to the half up here, over 4 times 2b to the 3/2. And this is all looking a little messy, but I can probably clear this up. Let's, for example, do the factors of 2 we have in here. So I've got a 2 out the front, then I've got a 2 to the half on the top there, and then on the bottom here I've actually got 4, which is 2 squared, and then I've got 2 to the 3/2. And you can see a couple of things happening. In fact, on the top line I've got 2 to the 3/2. That'll cancel with my 2 to the 3/2 on the bottom. I'm going to end up with 1 over 4 as part of my answer here. What about these factors of pi? I've got pi to the half on the top line, and then I've actually got pi to the half on the bottom line. So in fact they will cancel out just to give me 1. And then there's the factors of b that I've got here. So I've got b to the half here, and on the bottom line here I've got b to the 3/2. And you should be able to see there that I'm going to end up, in fact, that half and that 3/2 will just give me 1 over b. So my final answer here is actually 1 divided by 4b. That's actually, if I just put it up here, that's the expectation value of my square of position is 1 divided by 4b. Now before we finish, it's worth just double checking if these answers kind of make sense to us. One thing we might consider is that we actually have the main form, the spatial dependent part of our wave function here, if you like lowercase psi, we can just kind of pull that out, is equal to this a e to the minus b x squared. And you can see straight away there's a certain symmetry here. This thing is indeed itself an even function. If you were to think about this as a Gaussian distribution here, which basically looks something like this. And if I was to measure the position of a particle described by this wave function, it's just as likely to be out here at some negative value of x. So this was my psi here. Of course, psi squared is what I care about, but psi squared will look quite similar to psi in this case here. It's just as likely to be out here at some negative value of x as it is at some positive value of x. In fact, there's a complete symmetry about here. And so if I was to average in a large ensemble of particles like this, I'd expect just as often to have a positive x as a negative x. It would indeed average out to 0, which is what my calculation showed, that my expectation value of x would be 0. Of course, for x squared, it's not quite the same, because even though I'm more likely to be, just as likely to be at negative as positive, when I average all the squares of those, they're all positive numbers. So I might have to think a little bit more carefully about whether there's some way of checking whether this is indeed a good description here for my expectation value of x squared. One thing I should be able to check straight away is, does 1 over 4b have the right dimensions, the right units to actually measure a distance squared? And again, we come back and look at our initial relationship here. I've got an exponential function that has b times x squared up here. And that tells me that b times x squared must have no units. Remember, if I'm going to put that into a mathematical function, like an exponential here, this must have no units. Otherwise, if I change the units, I change the value. So this must be a dimensionless quantity, which tells me that the the units of b must be 1 over a length squared. So I can see straight away, just by looking at this function up here, that I can tell what the units this lowercase b constant must have. And that means, of course, that 1 over b will have units of length squared. Well, that's good. That tells me that this indeed has the right kind of units, at least. But what about the behavior? This kind of says that as b was getting larger, my expectation value of x squared should get smaller. And that might depend a little bit upon how much you're familiar with things like Gaussian functions. So let's just have a quick look here. Here's a diagram here showing a couple of Gaussian functions where the only thing we've changed is in fact the value of b. So we might say that this blue curve here has some value b1, and it turns out that if you then sketch out this red curve here that has a value of b2 that's actually larger than b1. And so we can see the width of this kind of distribution here gets smaller as that b value gets larger. So certainly that red distribution there has a much smaller width than this blue distribution here. So that tells us we have the correct behavior, that in fact as b increases we get a narrower distribution, and therefore we'd expect a decrease in this expectation value of x squared. So then we've been able to calculate those expectation values and even make sure that we've got some understanding as to why they have the values they have. There is another PhysCast that follows this one where we're going to do the same wave function but now calculate the expectation value of momentum and momentum squared. So you might like to watch that PhysCast after you finish this one.